here is the question that I asked in the previous part of this video lecture, and let's see how to answer it. I'm going to start by labeling things and drawing the free body diagram. And just notice that if the acceleration were 0, we would see that the force exerted upward by the spring is equal in magnitude to the gravitational force on the mass. That's why a scale works. It has to normally exert an upward force equal to the weight of the object. But that's not what's going on here because things are accelerating up, and so the spring must be exerting a larger force than the gravitational force on the mass. That gravitational force is 10 newtons, right? mg, 1 kilogram times 10 meters per second squared, roughly. So, I'm going to set axes, and here's the equation of motion. And note that we know that gravitational force is mg. You can solve that for the force exerted by the spring, and you're going to get 12 newtons, bigger than the gravitational force on the mass, just as we know it must be. But again, it might be nicer to see that graphically. Here's the graphical addition of the force vectors, and when we know that that gravitational force has a size of 10 newtons and ma is 2 newtons, then that shows us that the force by the spring must be 12 newtons. Let's finish up with one more example. And this is going to be a somewhat more explicitly two-dimensional example. So here is a skier going down a hill, and they are speeding up at a rate of 2.5 meters per second squared. And let's find out what the strength of the friction force is acting on this skier. So we're thinking about forces, and our knee-jerk reaction should be that as soon as we're thinking about forces, we should draw a free body diagram. So I'm going to do that. There is, of course, a gravitational force due to the Earth. The only thing the skier is in contact with is the hill, so there must be a perpendicular force due to the hill. And the skier is slipping on the hill, and so there will be a kinetic friction which opposes the slipping. The skier is going down the hill, so the friction force must be up the hill. And as always, I should draw the acceleration vector somewhere near the free body diagram. To do any calculations, I'm going to need to define components, and so I'll need to set axes. Here's some general advice on setting axes. You want to line your axes up with as many vectors as possible so that you don't have to break too many of them up into components. If I set tilted axes with my y-axis perpendicular to the hill, then I'm going to have 3 of my 4 vectors lined up with an axis, and the only force I'm going to have to break into components is the gravitational force. So I should do that. My other piece of advice is always set one axis in the direction of the acceleration if you know what direction that is. That's not always the best choice, but it is usually the best choice, so it's good to keep in mind as a fairly general rule. So that gives me axes that look like this. The next thing to do is write the equation of motion. So I'm going to write a sum of x components of forces and a sum of y components of forces, and I'm going to set those equal to the appropriate components of ma. So, in the x direction, I have a component of the gravitational force. So let me do the work to split that gravitational force into components. I know its magnitude is mg. And then I'm going to have components that point this way, perpendicular to the hill, and this way, parallel to the hill. There's the right angle, right? Remember, the vector you're splitting up into components is always the hypotenuse of the triangle you draw. The 30-degree angle is here. And so this is the x component here, and this is the y. Let me simplify my notation. I only have one perpendicular force, and so I'm just going to call it F perpendicular. I only have one gravitational force, so I'm just going to call it Fg. And I only have one kinetic friction, so I'm just going to call it Fk. And so this is Fgx, and this is Fgy. And if you do the trig, you'll see this is the opposite, and so it's mg sine of 30 degrees. And this one, be careful, it's negative mg cos of 30 degrees. And so now I'll put those in. I have an x component of the gravitational force, and the only other force with an x component is Fk, and its x component is negative its magnitude. And so that is all equal to max, and I'll come back to that in a moment. And now my sum of y components, I have F perpendicular, and I've already worked out I have minus mg cos of 30 degrees, and that equals may. And looking at the acceleration, I can see that its y component is clearly 0, and it points in the x direction, and so its x component is just its magnitude, a. And now we can see my unknowns are just Fk, which is the thing I'm looking for, and F perpendicular. I don't care about F perpendicular, but notice I could find it out of this equation. It would just be mg cos theta. People see that often enough, they tend to think of it as a general result for things on a slope. It isn't. If there was any other force that wasn't perpendicular or parallel to the slope, that would change what F perpendicular comes out to. We only ever know these forces by solving for them out of the equation of motion. Anyway, I will do that for Fk, which is what I'm actually looking for. Check the units. I have kilogram meter per second squared, and so that is indeed newtons. And plugging that into a calculator, you should find that it is 150 newtons.